Hello everyone. I hope you are doing good. Today's our topic is electrostatic potential and capacitance, example 2.2 to 2.3 and NCERT section 2.6, that is equipotential surfaces. So let's begin. Disclaimer. The images, text and other material used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated through generative AI, which is experimental. So here is the index that the topics we are going to discuss today. Firstly, we will discuss two examples based on our previous topic, electrostatic potential, that is NCERT example 2.2 and NCERT example 2.3. Then we will discuss the section NCERT section 2.6, that is equipotential surfaces. So here is the first example, example 2.2, which is two charges 3 into 10 is power minus 8 coulomb and other is minus 2 into 10 is power minus 8 coulomb are located 15 centimeter apart. At which point on the line joining the two charges is the electric potential 0? Means we have to find the point on the line joining these two charges where the electric potential becomes 0 due to these two charges. Take the potential at infinity to be 0. Okay, so firstly we have to place the charges using the coordinate system. So firstly we will place the positive charge, this positive charge on the origin and the other positive charge on the x-axis with the distance of 15 centimeter. Then the line joining of these two charges is taken to be x-axis. The negative charge is taken to be on the right side of the origin. Positive charge at origin and this negative charge will be at x-axis, positive x-axis at the distance of 15 centimeter. So this is the diagrammatic representation. Point O, that is origin, and the positive charge, that is 3 into 10 is power minus 8 coulomb, is placed at this origin, and this is the x-axis, positive x-axis, and this negative charge is placed at point A at a distance 15 centimeter from this positive charge. This is the P point. This is the P point where we assume that the potential due to these both charges is 0. The effect of these two charges, this positive charge and negative charge, and the net potential at this P point is 0. Okay, the distance of this P point from this positive charge is x, or this P point can either be on this line between these two charges, positive and negative, or this P can be on the right side of this negative charge. Means it can be between these two charges or it can be beyond this negative charge, but it can never be before this positive charge. Why? I will explain. Okay, let P be the required point on the x-axis where potential is 0. If x is the x coordinate of the P, obviously x must be positive. So x is the distance of P point from this positive charge. There is no possibility of potentials due to two charges adding up to 0. Means for x less than 0. Means this P can never be in the left side of this positive charge for this problem. Why? Because this positive charge has greater magnitude than this negative charge. So potential, 0 potential condition can be on this line or can be in the right side of this A point. Cannot be in this side because this has more magnitude. So the 0 potential will be on the right side of this positive charge only. So there is no possibility of potentials due to the two charges adding up to 0 for x less than 0. So x, negative value of x is not possible here. What is x? X is the distance of this P point from this positive charge. I am again repeating. So if x lies between O and A, if x lies between O and A, there is two cases now we will discuss. If this P point is between O and A, or if this P point is beyond this A. There are two cases. First case is if this P lies between this O and A. Then what is the distance of this P point from this O? X. What is the distance of this P from A? 15 minus x. So if x lies between O and A, we have 1 by 4 pi epsilon naught 3 into 10 is power minus 8 x into 10 is power minus 2. Means this is the potential at P point due to this positive charge. 1 by 4 pi epsilon naught. This is the positive charge upon what is the distance of this positive charge from P? X into 10 is power minus 2. Minus. Now, minus 2 into 10 is power minus 8. This charge, this minus is due to this negative charge. We are adding the potentials due to these both charges and equating with 0. We have to find the point now where sum of potential due to these both charges becomes 0. So we are adding the potential due to these both charges. This is the potential due to this charge and this is the potential due to this charge. 2 into 10 is power minus 8 upon what is the distance of this A from this P point? 15 minus x into 10 is power minus 2. Then the sum of these potentials is equal to 0. So now we will solve this for x. So 3 by x minus 2 by 15 minus x equal to 0. So what is the value of x now? Which gives x equal to 9 centimeter. So the point P lies on the x-axis at distance 9 centimeter from the point O, from the origin, from the positive charge. This is the first case. Now second case, if P lies beyond A, means P is not between these both charges but in the right side of negative charge. If x lies on the extended line OA, now what is the condition now? Now, what is the distance of P point from origin? We will take it as x. But now if P is beyond A, so distance of this P point from A is x minus 15. Now this term changes because it is on extended line. So P point has a distance from the positive charge x. Now P point has distance from A point is x minus 15. And this negative charge is due to negative charge, this 2. Now solving this, we will get x equal to 45 centimeter. Now these two values, these are the two values, x equal to 9 centimeter and x equal to 45 centimeter. Now x equal to 9 centimeter lies between these both charges, but x equal to 45 centimeter lies beyond A point. So these are the two possible values of x for which the potential on x-axis is 0 due to these both charges. Okay, thus electric potential is 0 at 9 centimeter and 45 centimeter away from the positive charge on the side of negative charge. Note that the formula for potential used in the calculation required choosing potential to be 0 at infinity. It is also mentioned in the question that you have to assume potential to be 0 at infinity. That is our convention, because without reference, potential is not physically significant. So we have to define the reference first. So in question also given, and by default we also take potential to be 0 at infinity. So these all calculations are made based on the assumption that potential to be 0 at infinity. Okay. Okay, so next example. This is our next example. So here there are 5 parts of this example. So you can also write this question side by side so that when I will turn up to answer, you will have question then. So figure 2.8a and b shows the field lines of the positive and negative point charge respectively. So these are two figures given. One is positive charge and one is negative charge. This is the electric field lines due to positive charge, which are in the direct. What is the configuration of electric field lines around a point charge? For positive charge, it is radially outwards, and for negative charge, it is radially inwards. Now, these are the points P and Q. P is closer to this charge, Q is farther apart. And for this negative charge, these 2 points A and B. A is closer than this negative charge and B is farther apart from this negative charge. These are 2 diagrams. Okay, first part of this question. Give the signs of potential difference Vp minus Vq. Potential at P minus potential at Q. Give the sign of this potential difference and Vb minus Va. You have to give the sign of potential difference. That potential difference is positive or potential difference is negative. This is first part. You can write it side by side. Second part. Give the signs of the potential energy difference of a small negative charge between the points Q and P and A and B. Again, now they are asking sign of potential energy of small negative charge. Now, we are taking test charge as negative. By default, we took test charge as positive. Now, the test charge, we are taking negative charge. What is the potential energy difference from point Q and P and from point A and B? Third part. Give the sign of the work done by the field in moving a small positive charge from Q to P. Now you have to give the sign whether the work is positive or negative while we moving small positive charge from Q to P. Fourth part. Give the sign of the work done by the external agency. External agency means external force that we are applying. Give the sign of the work done by the external agency in moving a small negative charge from B to A. You have to focus on the charge, whether they are saying positive charge or negative. And if it is not mentioned, then you have to take by default positive charge. But if it is mentioned negative charge, you have to consider that polarity of the charge. Now, give the sign of the work done by external agency in moving a small negative charge from B to A. And fifth part, does the kinetic energy of a small negative charge increases or decreases in going from B to A? Now, if we move a negative charge, small negative charge from B to A, whether its kinetic energy decreases or increases, you have to tell that. So these are the 5 parts of this question. Now, one by one, I will answer that. Okay, this is the diagram again. First part. What was the first part? Give the signs of potential difference Vp minus Vq. Now, we know that potential is inversely proportional to the distance from this charge. For a point charge, what is the potential? What is the variation of the potential with the distance? Potential is inversely proportional to R, because for point charge, potential is equal to 1 by 4 pi epsilon naught Q by R. So it is inversely proportional to R. So now the charge was not given in the first part. So we have to take test charge as positive. Now we are moving from Q to P. So when we move from Q to P, P is closer, means R is less for P. So potential at P is greater than Q. R is less than P than Q. So because potential is inversely proportional to the distance. So what is the potential? Potential at P is greater than potential at Q. Thus Vp minus Vq is positive term. Because potential at P is greater, so Vp minus Vq is positive. This is understandable. Second thing, Vb minus Va. Now, this is negative charge. We are moving positive charge from B to A. Now, this negative charge will, now the condition changed. Condition is changed. Here is positive charge and we are moving also, test charge is also positive. Now, test charge is positive, but the source charge becomes negative. Now, it will attract this test charge. Now, the potential, what is potential? Is inversely proportional to R. But now the negative signs also appears. Means potential at B is less negative than the potential at A. Okay, I will explain again. First part, we know that potential for a point charge is equal to 1 by 4 pi epsilon naught Q by R. So potential varies inversely with the distance from the charge. Because P is closer to this charge, so P has greater potential. Vp minus Vq. So we have to tell the sign of Vp minus Vq. So since Vp is greater than Vq, so Vp minus Vq is positive. Also Vb is negative. Now, this charge is negative and we are moving a positive charge from B to A. Now, potential at A is more negative because the negative sign appears in the formula. V equal to 1 by 4 pi epsilon naught Q by R. Now Q is minus Q. So potential at A, it is varying inversely with R, na? So it is varying inversely with R. So potential at A should be greater, but there is a negative sign, so it is more negative. Potential at A is more negative and potential at B is less negative. So Vb minus Va. Vb minus Va. Vb is less negative, Va is more negative. Okay, you can take example here. Vb is minus 2 and Va is minus 4. Vb is minus 2 means less negative. Va is minus 4 is more negative. So minus 2 minus minus 4. What it becomes? Minus 2 plus 4, which results in positive value 2. Okay, so this is Vb minus Va is positive. Now, second part. What was second part? Give the sign of potential difference, potential energy difference of a small negative charge between the points Q and P and A and B. Now, a small negative charge will be attractive towards positive charge. Now, we are using now test charge as small negative charge. Now, if we place negative charge at Q, this positive charge will attract it. Now, we are not applying any external force. We are not going against the field because this positive charge will attract this negative charge. So, we are not applying any opposite force, external force against the electric field. We are providing the supportive force. So, if a negative charge is to be moved from Q to P, so potential energy at P will be less. Potential energy at Q will be greater. Remember one thing, if we are moving a charge, any charge against the electric field, we will have to do work. The work and hence potential energy will be positive. If we are moving a charge in the electric field in the same direction, we are supporting the force. We are not doing any work against the electric field or electric force. We are doing the work in support of that force. So that in that case, work is negative and hence the potential energy is also negative. Okay. Now, a small negative charge will be attracted towards the positive charge. The negative charge moves from higher potential energy to lower potential energy. Okay. So positive charge, now Q negative charge is at Q. So positive charge will attract it. Okay, the negative charge, now it is moving from Q to P. At P, the potential energy is less. It is moving from higher potential energy to lower potential energy. Because we are moving in the support of the force. It is attracting, na? It is attracting Q. It is not repelling Q. So we are not doing any work against it. Okay, so potential energy is decreasing from Q to P. Okay, therefore the sign of potential energy difference of a small negative charge between Q and P is positive. Okay, minus P, UP minus UQ is positive. Similarly, when we move from B to A, negative charge, here source charge is also negative and test charge is also negative. So it will repel it. We are doing work against the electric field of this negative charge, negative source charge. We are doing work against the electrostatic field. So potential energy at A will be greater than the potential at B. So sign of potential energy differences will be positive. Okay. C. What was the question C? Give the sign of the work done by the field in moving a small positive charge from Q to P. Now work done from Q to P. Small positive charge. Now this is positive charge and test charge is also positive. So we are moving a positive test charge from Q to P. So this source charge will repel it. We are doing work against the electrostatic force. So this work done is stored in the form of potential energy, and that work done is positive because we are doing against the electrostatic force. If we are doing work against the electrostatic force, it will be positive. If we are doing in the same direction, or if the work is done by the conservative forces, we are not applying any external force. The work is done by the conservative forces. If I place here negative sign, here if I place here negative charge, it will attract it. It will attract it towards itself. We don't have to apply any force. So then potential energy decreases and work is done by this positive charge. Work is done by the conservative forces. We are not doing any work. If there is positive charge, we have to, from moving positive charge from Q to P, we have to do the work against the electrostatic force. That work done is positive and hence potential energy difference is also positive. Understood? So C, in moving a small positive charge from Q to P, work has to be done by an external agency. As I have mentioned, we have to do the work, external work, against the electrostatic field or electric field. Therefore, work done by the field is negative. Work done by the field is negative, but work done by us is positive. Okay, they are asking work done by the field. You have to remember that thing also. Work done by us is positive. Work done by the field is negative. Or you can see with the basic fundamental concept that if the displacement and force is in the opposite direction, then the work done is negative. So field is in the direction radially outwards. We are moving the charges from Q to P. Okay, force on this test charge is in outward direction. We are moving this positive charge in the inward direction. So work done by the field is negative here, because force due to the field is in outside direction and displacement is in inward direction. So work done is negative. But work done by us, we are doing the external work in which direction? Against this electrostatic field. We are applying the force against the electrostatic field, and also the displacement is in this direction. So work done by us is positive, work done by the field is negative. D part. Give the sign of the work done by the external agency. Now question is reversed. Firstly, they asked work done by the field. Now they are asking work done by the external agency in moving a small negative charge. Also, polarity of charge is reversed. They are now giving negative charge, and work done by the external agency is being asked from B to A. Now we are moving this charge from B to A. Okay, negative charge. And this is also negative charge. Electric field has direction radially inwards. And force on the negative charge due to this electric field is in outward direction. Electron, negative charge particle. Electron experience force in the opposite direction of electric field. This is, you all know. Okay, so electron will, or that negative charge will experience the force in the outward direction, in the opposite direction of electric field. But we are applying the force in the inward direction from moving this negative charge from B to A. And displacement is also in this direction. So what is this? Work done by the external agencies? Positive. Okay, and work done by the field is here negative. Okay. E part. Does the kinetic energy of small negative charge increases or decreases in going from B to A? Now again, this is the basic fundamental concept. This here, if we place B, negative charge on B, this is also negative charge. There will be repulsion. If we give any velocity here towards this negative charge, due to repulsion, velocity will decrease or increase? It will decrease. So kinetic energy will also decrease. Due to force of repulsion on the negative charge, velocity decreases and hence kinetic energy also decreases in going from B to A due to force of repulsion. Force of repulsion will decrease the velocity, hence the kinetic energy of the particle. So these are the examples. Now the very important topic, that is equipotential surfaces. So what are equipotential surfaces here? By the name equipotential means the potential should be equal. Surfaces. Okay. Now, okay. Equipotential surfaces. Surfaces at which the potential remains same. Means we will take any surface, and if the potential on whole surface is same, we will consider that surface as equipotential surface. Okay. So surface at which on any point of this surface potential is same. Equipotential surface. This surface is equipotential surface. Okay. So firstly, we will see some charge configurations and what are the equipotential surfaces for this charge configuration. For a single point charge, what is the equipotential surface here? Okay, for a single charge, now see, we know that for point charge, formula for potential is V is equal to 1 by 4 pi epsilon naught Q by R. Q is the charge, Q remains constant, 1 by 4 pi epsilon naught is constant. What is varying when we move from here to here in outward direction? R is varying. So potential depends upon, potential is inversely proportional to distance from this positive charge. If we fix this distance, if we assign any value to this distance and fix this distance around this positive charge, what surface will form? Sphere. Because in any direction from this positive charge, if we take any constant value for R and we will move in any direction and mark that R, and if we form a surface from this, the locus of these all points will become a sphere. So Means if this is positive charge Q, I will fix any value for R. Suppose this is R. This is same value R in this direction. This is same value of R in this direction. This is same. The locus of these points will form a circle in 2 dimension, but in 3 dimension, what surface will form? Sphere. Okay. So this is this surface. What is this surface? Sphere. So sphere is the equipotential surfaces around a positive charge. Okay. Potential is inversely proportional to distance. If the distance is less, potential will be more. Means if the distance is close to this positive charge, potential will be more at this point. As we are moving away from this positive charge, potential decreases because R is increasing. Because they have inverse relation. Potential has inverse relation with the distance from this positive charge. As the distance increases, potential decreases. So potential will be more when we are close this positive charge, and potential will be less if we are far away from this positive charge. You can also see the configuration of these equipotential surfaces. These are closely spaced. These are closely spaced. But when we move away from this positive charge, equipotential surfaces, the distance between the equipotential surfaces increases because the potential is decreasing. Okay. For a single charge Q, equipotential surfaces are spherical surfaces centered at the charge, and B, electric field are the radial starting from the charge if Q is equal to 0. These are the comparison. These are equipotential surfaces. These are electric field lines. Now we will also see the relation between equipotential surface and the electric field. What it means. Okay, firstly we will see this. An equipotential surfaces maintains a constant value at all points on it. This thing I have already mentioned, that equipotential surface maintains a constant potential at all points in it. Means if I take this sphere, any sphere out of these, thus if I take this sphere, okay, so the potential value of potential on any point on this surface will be same. This is the real meaning of equipotential surface. For a single charge Q, the potential follows. This is the equation I have mentioned. V is equal to 1 by 4 pi epsilon naught Q by R, indicating V remains constant when R is constant. If we fix any distance R and make a surface out of points in all direction, it will make a surface that is equipotential surface. Okay, if we fix R. So V remains constant on this surface because R is constant. Okay, therefore equipotential surface for a single point charge form concentric spherical surfaces centered at charge. Yes. Positive charge and negative charge both have equipotential surfaces, similar equipotential surfaces. But the direction of electric field line is different. Okay, direction of electric field line is different. In the case of positive charge, it is radially outwards. In negative charge, it is radially inwards. But equipotential surfaces for both these positive and negative charge will be spherical surfaces. Okay. For a single charge Q, electric field lines extend radially, either starting from or ending at the charge based on whether Q is positive or negative. This thing came that only electric field difference is between positive and negative charge. For positive charge, it is radially outwards, and for negative charge, it is radially inwards. But equipotential surfaces are same. The electric field at any point is perpendicular to the equipotential surfaces through that point. This principle applies universally for any charge configuration. This is very important point. That electric field, direction of electric field is always perpendicular to the equipotential surface for any charge configuration. Whether it is point charge, whether it is linear charge, whether it is surface charge, whether it's volumetric charge. Any distribution, any charge distribution, this principle applies. Electric field is always perpendicular to the equipotential surface. What is the reason? We will also come to that point. Okay, for surface charge density, this is the surface charge. These plates are, this plate is charge. Okay, so electric field, this is uniform electric field. Sorry, this is uniform electric field. So uniform electric field has same value at all points. Okay, means this is uniform electric field. These are the lines of electric field. Okay, this is uniform. Now, potential, what is the potential at this point? Suppose this is uniform, which surface charge configuration produce uniform electric field? That is sheet. That is charge. Charge sheet will produce the uniform electric field. Now, what are the equipotential surfaces from these points? Okay, so equipotential surfaces will be these perpendicular sheets. This perpendicular sheet means from this point to this point, at this perpendicular sheet, potential will be same. After some distance, if we again threw a perpendicular sheet on this uniform electric field, the potential on this sheet will be equal. Okay, for uniform electric field, the equipotential surfaces are perpendicular sheets. Equipotential surface for a uniform electric field. The perpendicular relationship between electric field and equipotential surface can be proven simply. If the field wasn't normal to the equipotential surface, it would have a component along the surface. This is the reason what we have studied before in the previous slide, that why it is always perpendicular to the equipotential surface. This is the reason. If it is not perpendicular to the equipotential surface, if the electric field is any orientation, is oblique to the equipotential surface, it will have two components. One is perpendicular to the equipotential surface. Second one is parallel to the equipotential surface. If there is a component parallel to the equipotential surface, then our statement goes wrong. What we stated, that equipotential surface, there is a constant potential all over the surface. But if there is a component, horizontal component along the surface of the equipotential surface, then we have to move a charge. If we want to move a charge on equipotential surface, then we will have to apply the work against that component of electric field, which is complementary. Moving a unit test charge against the field component would require work. If there is any component along the surface, if the electric field is not perpendicular to the equipotential surface, then there will be a component of electric field along the equipotential surface. However, this contradicts the definition of an equipotential surface. Now, the potential on equipotential surface is same at every point. So we don't have to do any work to move a charge on the equipotential surface, because potential difference between 2 points on equipotential surface becomes 0. Potential difference between 2 points on equipotential surface is 0, because potential is all over same. Okay, so work is Q into potential difference. So work is also 0. So we don't have to do any work to move a charge on the equipotential surface. Okay, but if the electric field is not perpendicular to the equipotential surface, then it will result in component along the equipotential surface. Now, There is electric field along the equipotential surface. Now we have to move a charge. This electric field will obstruct the path of the charge. This will apply some force. So now we have to do work. So this thing contradicts the definition of equipotential surface, where no potential difference exists between the points and no work is needed to move the test charge above the surface. Therefore, this thing comes from this definition that electric field is always perpendicular to the equipotential surface. It must not have any component along the equipotential surface according to its definition, because we don't want any work to move a test charge along the surface. Okay. Now, does the electric field must be perpendicular to equipotential surface at every point? For a uniform electric field E aligned with the x-axis, the equipotential surface are planes perpendicular to x-axis, parallel to yz plane. Equipotential surfaces provide an alternative visualization method alongside electric field lines for understanding charge configuration, as shown in the figures for cases including electric fields, dipoles, and two identical positive charge. Now there are some more charge configuration for which equipotential surfaces are shown. First one is, this is negative and positive. This is dipole. For dipole, equipotential surfaces are in this form. You can also draw this. For dipole, what is the electric field lines? Electric field lines will originate from this positive charge and end at this negative charge. You know how to draw the electric field lines for a dipole. Now, you have to draw a surface around these two charges which is always perpendicular to the electric field lines. Then you will result in these surfaces, these type of surfaces. These are not circular, these are not spherical, these are elliptical. Okay, in this direction. You can draw also. And for a similar charge, for negative negative or for positive positive, equipotential surfaces are in this direction. Firstly, you have to draw the electric field lines. What is the electric field lines configuration for this positive positive charge? Then you have to draw surface which is perpendicular to each and every electric field line. Then you will result in this type of surfaces. Okay. Some equipotential surfaces for dipole, two identical positive charges. Yes, where electric field lines are closer, their equipotential surfaces are also closer. Okay, this is the region of higher electric field and this is the region of higher potential. Okay, so when the equipotential surfaces closer to the charge are more closely spaced and farther apart from the charge is farther apart. Distance between equipotential surfaces increases when we move farther apart from the charges. Okay, now our last topic, and it is also very important topic, that is understanding the relation between the field and potential. This will help you solving many numericals. Okay, this type of the numericals based on these topics are also very important. So we will assume these two equipotential surfaces, A and B. A having potential V and this B equipotential surface have potential V plus delta V. Means potential somewhat higher than this potential. Okay. So this is A equipotential surface, this is B equipotential surface. So this is P point and electric field having direction in the upward direction. And this is the delta L. This is the distance between these two equipotential surfaces. Okay. Now consider two closely spaced equipotential surfaces A and B with potential values V and V plus del V, where del V is the change in V in the direction of the electric field E. Now let P be a point on the surface B. P is the point on the surface B and delta L is the perpendicular distance of the surface A from P. Imagine that a unit positive charge is moved along this perpendicular from surface B to A. A unit positive charge is moved from this point P to this A in downward direction against the electric field. Now electric field is in this direction. We are moving positive charge in opposite direction from B to A. The work done in this process is E into dl. Work done is Q E dl. Q E delta L. Why there is not Q here? Because we are taking unit positive charge. Q is 1. So work done is E into delta L. Now this work equals the potential difference. What is the work done here? Equal to Q into potential difference. Q here is 1 unit positive charge. So work equals to potential difference here. So EDL is equal to V minus V plus delta V, which is minus delta V, because this positive charge is moving from higher potential to lower potential. So the change in the potential is minus del V. So E will become minus del V by del L. Since del V is negative, which is this, del V is negative, so positive value for this is this. So we can write this equation as this also. This is the positive value. This is the magnitude of electric field. But actual expression is this, E equal to minus del V by del L. What does that mean? We does arrive at two important conclusions concerning the relation between electric field and potential. What does that mean? What is that negative sign mean? First one, electric field is the direction in which potential decreases steepest. What is that negative sign means? Electric field is in the direction in which the potential decreases steepest. This statement means the electric field is in the direction of decreasing potential. In the direction of decreasing potential. And second major conclusion is its magnitude is given by the change in the magnitude of potential per unit change in the displacement normal to the equipotential surface of the point. What is the magnitude of the electric field? It is the change in the magnitude of potential per unit displacement normal to the equipotential surface at the point. And what is the direction of electric field? In the direction of decreasing potential. Okay, these are the major two conclusions. So thank you. I hope you understand the topic.